In this video, we look at the point location problem, and we try to give an alternative solution using a different paradigm of algorithm design. And the paradigm we're going to look at is randomized incremental. Okay, so what's the problem again? So we have a planar subdivision with n line segments, and we want to pre-process for point location queries, and we want to get linear space and log n query time. So the first idea is to create a refinement, because the input is kind of a complex object, and if we can break it down into smaller and more manageable pieces, then we have a better hope of solving it. One way to do this is to look at every vertex, and we can draw vertical lines up and down from this vertex. What this would do is to decompose the input in a bunch of slabs. So for example, like this slab over here. When I look at this slab, when I look at this inside of it, it's very nice, right? So I have these line segments that cross the slab, and we can always do search between them, because I could, if I have a query point, I could do binary search, and I could do above and below here, so it's below, so I go here, here is above, and so on, right? So using the above and below test, I could essentially find the region where a query point lies. The problem with this kind of refinement is that the input size will be n squared, right? Because when you draw a vertical line from a vertex, it could intersect all the line segments in the input. So in the worst case, this could give us n squared solution, which is not desirable. So now the question is a refined subdivision of n of size linear, which is simpler, and it's made of simple objects. And the answer is yes, and the idea is very simple. We just do the same thing, except that the first time we hit an obstacle or a line segment, we stop the vertical line. So basically something like this. Like this. So these red marks, the red line segments, are the ones that we are interested in. And if I get rid of the remaining blue ones, this picture looks like this. So now from every vertex, I shoot an upward ray and a downward ray, and the first time it hits line segment, input line segment, it stops. Okay. What is the result of this subdivision? This is called a trapezoid subdivision, because every region will be a trapezoid. You can easily see this from the picture, but basically a simple proof is that pick any vertex. Let's say, I don't know, this vertex. There is an edge going up, and there's an edge going down. So let's just follow this edge going up. It will hit another trapezoid, and at some point when I walk along this upper edge, I will hit another vertical line, either because I meet a vertex that is going down, or because I will meet another vertical line that is coming from another vertex, right? So these two are examples of that. In either case, this region will be enclosed by two parallel lines, two vertical lines. So therefore it is technically, it's called a trapezoid. Okay, so what does this achieve for us? This turns the input from being a bunch of disjoint line segments to being a set of trapezoids. Now the question is, can I do point locations in a set of trapezoids? And this is the next thing I'm going to solve. But before going forward, pay attention that even this decomposition is unobvious, right? Because how do I turn a bunch of disjoint line segment into a set of trapezoids? To do that, I need to figure out what is the first line segment hit. So it looks like I need to solve point location problem to be able to build a point location data structure. Seems like a circle problem, but the solutions that we're gonna explore is gonna do both things at the same time. It's both gonna create a trapezoid decomposition and a point location data structure to solve it.